Good afternoon, everyone. I'm BELKACEMI, PhD student at l'École des Mines de Paris. I work in collaboration with Jacques, and I will present to you some results obtained during my PhD project entitled Characterization Methodology of Pipeline Weld Joint Under Hydrogen using subsite specimen. So this PhD project is a part of a Messier chair held by Professor Jacques and Yazid MADI. If I have to translate the meaning of Messier, it will be meaning simple for in-service monitoring of structure with application to hydrogen transportation. The main objectives here is to develop a new methodology for the mechanical characterization based on subsite specimen and then extend this procedure to study the hydrogen embeddment of structure. So the material used in this study is a vintage X52 low carbon steel and its longitudinal submerged arc welding. So concerning the chemical composition, we have presence of manganese and silicon, but we notice also the presence of sulfur, which will be the reason of the formation of some complex inclusions. So the microstructure of the base material here, it's a ferrite perlite microstructure, and the BESSON analysis showed that we have no preferred crystallographic orientation. So we also studied the double pass submerged arc welding. As we can see from this micrograph, so we have the weld metal in the center. This weld metal is divided into two sub-regions depending on its microstructure. We have the weld metal top and we have the bottom. Adjacent to the weld material, we have the heat affected zone, which can also be divided into mainly two sub-zones. We have the heat affected zone 1, which presents a circular ferrite, and we have heat affected zone 2, which presents ferrite perlite microstructure. The inclusion analysis in the base material shows the presence of large and elongated inclusions. These inclusions are of two types. So we have the silicon manganese oxide, and we have also the presence of elongated MNS, especially in the T and L direction. The volume fraction of the inclusions in the base material is about 0.23%. For the weld material, we have only the presence of small and spherical inclusions. These inclusions are, so we have only silicon manganese oxide, and the volume fraction of inclusions is about 0.70%. We have also performed some BST analysis to get some information about the microstructure of the weldment. So here we have the inverse fold figure and the grain orientation spread of the weld metal top and weld metal bottom. If we compare the inverse fold figure, we can see this difference in the grain shape. So we have a columnar grain in the weld metal bottom, and we have a polygonal grain in the weld metal bottom. And if we compare the grain orientation spread, which gives us some information about the strain, the residual strain in the material, we see that the weld metal top presents a higher misorientation angle, which means that in the weld metal top we have more residual strain than in the weld metal bottom. We have also performed the micro-hardness mapping using more than 9,000 indentation. And when we look at these maps, we see that a part of heat affected zone shows the highest hardness in the weldment. The hardness is between 190 and 210. And we also observe that the weld metal top presents higher hardness than the weld metal bottom, and the weld metal bottom and the part of heat affected zone, which is called here subcritical heat affected zone, present the lowest hardness in the weld joint. When we look at also to the extreme, to the right extreme of this map, we see that we have a difference in the micro hardness of external and internal subsurfaces compared to the center of the thickness. To confirm that, we have done some hardness variation far away from the weldment, and we see that we have this difference in the micro hardness between external and internal subsurfaces compared to the center of the thickness. So now, if we take into account this heterogeneous microstructure, we propose to use subsite specimen for the mechanical characterization. So we have chosen to use subsite concise specimen with a diameter of 1.2 millimeter and the length gauge of 2 millimeter. And we have chosen to use subsite specimen with 4 millimeter thickness. The subsite concise specimen are extracted from the base material and the weld material in the transverse direction. And for the heat affected zone, the subsite concise specimen are extracted parallel to the heat affected zone. We have done the same thing with subsite distal specimen, where the specimens are extracted in the base material and the weld material so that the load is applied in the transverse direction and the crack propagates in the direction of heat, except for the heat affected zone, where we extract the specimen so that the crack propagates parallel to the heat affected zone. So the subsize specimens are tested using new facilities and new methodology. Here I present a modified servo-direct tensile machine test equipped with specialized pressure chamber. This chamber is equipped with 4 sapphire windows, allowing us to use the real-time optical extensometry based on the edge tracing technique. And this methodology allows us to track the minimum radial contraction during tests and monitor it from the beginning to the end. And for the fracture toughness specimen, we can measure the load line opening displacement. We also have the gas analysis system, which allows us to ensure a pure gas inside the chamber. So we can measure the level of oxygen and the level of moisture. So more details about this setup and the methodology are well explained in the latest publication by MADI that was published 2 months ago. So here I present the effect of hydrogen on the tensile properties of the base material. We have performed tests under air, 100 and 200 bar, and we can observe that regardless of the pressure, the yield strength and ultimate tensile strength remains unaffected. But we can see that we have a strong effect on ductility. Here Z refers to the reduction area, and we have in the right the hydrogen embrittlement index. So we see that the ductility decreases with increasing the pressure, the hydrogen pressure, and the hydrogen embrittlement index may reach 60% under 200 bar. Here are the results of the effect of hydrogen on the tensile properties of the weld material. So we have the yield strength, tensile strength, under air 100, 200. And what we see is that the weld metal top exhibits higher yield strength and ultimate tensile strength than the weld metal bottom due to differences in the microstructure. And we also see that regardless of the pressure, the yield strength and ultimate tensile strength remains unaffected. But we also see that we have a strong effect on ductility. When we compare tests under air and tests under 100 hydrogen, we see that we decrease the ductility of approximately 50 to 60%. And when we compare tests under 100 and 200, we don't see any much further workload. Here I present a specific case of the heat-affected zone. So we have performed tests under air, but also tests under 100 hydrogen. And we can see that we have a strong dispersion results. This dispersion are in terms of yield strength and ultimate tensile strength, but also we have a strong dispersion in terms of ductility. When we try to explain this difference in yield strength and ultimate tensile strength, we see that it's mainly due to the difference in the microstructure. If we take the example of the specimen here plotted in the black line, we see that the specimen presents the acicular ferrite, which gives him higher yield strength and ultimate tensile strength. And when we compare it to another test performed under air here in green line, we see that the microstructure presents ferrite microstructure. So here we have, let's say, a strong effect between the microstructure and mechanical behavior. And when we try to explain why the ductility is much lower compared, for example, to the base metal or the weld metal, we see that when we compare these 2 specimens, we see the presence of large inclusion bands all along the diameter. These bands are not present in this sample, for example, and this is why we have much more ductility compared to the other specimens. And when we look at the tests under gaseous hydrogen, we also see that we have hydrogen embrittlement by the presence of quasi-cleavage. We can also here see the presence of amines inclusions elongated in the L direction, and we see here the presence of the inclusion bands. So here there is a combination between the hydrogen effect and the high amount of inclusions. Here are the effect of hydrogen on the fracture toughness of the base material. We have performed tests under air, under 30 bar, 60 bar, 100 and 200 bar. And we can see that the fracture toughness decreases with increasing hydrogen gas pressure till 60 bar, and beyond 60 bar, the hydrogen embrittlement reaches a plateau, which suggests that the base material has reached a saturation point where no more hydrogen embrittlement occurs. If we look at the fracture toughness, So if we look at the specimens under air, we see the typical ductile propagation. So we see the presence of large dimples associated with the presence of large inclusions. And we also see here the presence of blending zone in the initial crack tip, which is referred as stretch zone width. This blending zone becomes much more difficult to observe under 30 bar, and this blending zone does not exist under 60 bar. If we look at also to the tests, if we compare the tests under 30 bar and 60 bar, we see that under 30 bar, we have a mixed fracture mode. So we have the presence of dimples, but we have also the presence of quasi cleavage. And now when we look at the specimen under 60 bar, we can see that we have almost 100% of quasi cleavage. And beyond 60 bar, we have seen that we have this saturation point. Here are the hydrogen effect on the fracture toughness of the weld material. So I remember you that we have weld material top and weld material bottom. We have tests under air 100 and 200 bar. If we compare the weld metal top and weld metal bottom, you can see that the weld metal bottom shows a higher fracture toughness than the weld metal top under air, but also under gaseous hydrogen. We also see that as the hydrogen pressure increases, the fracture toughness of both weld metal top and weld metal bottom increases, and the hydrogen embrittlement index may achieve 70% under 200 bar, while we have only 30% of the hydrogen embrittlement index under 100 bar. If we look at now to the fracture surface, so here we have a fracture surface under air 100 and 200 bar. Under how we have the typical ductile propagation. The dimples here are much more small than what we have seen in the base material. We have also the presence of the blending zone here in the crack tip, in the initial crack tip. This blending zone does not exist under 100 and 200 bar. If we compare now 100 and 200 bar, we see that we have in the two cases, we have the mixed fracture mode. We have the presence of dimples, but we have also the presence of quasi cleavage. And the difference between 100 and 200 bar is the fraction of the quasi cleavage between the two species. Here I present another, the last example, which is the hydrogen effect of the fracture toughness of the heat affected zone. So we have tested a specimen so that the grade propagates forward to the heat affected zone, and we see that we have a strong dispersion in the results. If we compare, for example, the two black lines plotted, which are two tests tested under air, we see that we have a big difference in the two tests, mainly due to the differences in the microstructure. And we have also some dispersions under 100 bar, which are also linked to the differences in the microstructure. So to conclude, we have seen that the characterization using subside specimen are successfully performed using a new real-time optical trace technique. We've seen that the hydrogen gas pressure does not affect the yield strength and the ultimate tensile strength, but strongly affect the ductility of all our material. We have seen that for the base material, we reach a saturation point beyond 60 bar. And when we compare the fracture toughness of all our materials, we see that the heat affected zone or part of heat affected zone seems to have the lowest fracture toughness resistance in the X52 low carbon steel. Thank you for your attention.